going to look at second part and third part together because they are not different questions, okay? They are interrelated. So first, what I have done, I had a look at the data booklet. Because to calculate these values, I have to look at the data booklet. So from the data, I copy the values as I have, right? Now, what I have to see is what I'm being asked. So I have AL3 plus AL, SN4 plus SN2 plus, okay? This is what all I'm given. I'm not being told which one is the reactant, which one is the product. So I'm just going to write something over here. So when we are not told which species is acting as reactant, and which one is acting as product, the more positive of equation get reduced and the other gets oxidized. So which one is more positive over here? It is the SN4 plus. So equation number 2 is left as it is, but equation number 1 is reversed. So here I need to reverse the equation number 1. It is going to become Al, reversible sign, Al3 plus 3 electrons. We also need to cancel the electrons. So if they are not the same, we look for a common factor. So here the common factor is 6, I think so, isn't it? So 3, 2. Okay. So multiply by equation number 1 by 2 and equation number 2 by 3. One is reversed. Okay, so here this equation reversed and by 2. Here this one only multiply by 3. Why we are multiplying by 2 or 3? This is to balance the number of electrons. Okay, so I hope that now it is fine. So when you are going to reverse this one, it is going to become plus 1.66 volt. So this calculation, if this is by using formula, for those who have problem by the formula, you work out as I have told you, you reverse and you multiply, you're going to get this equation, and then the E naught value is going to be equal to, now it becomes very simple to work out, it's going to become plus 0.16 plus 1.66. Okay. So you get 1.82 equals just like you obtain it in second part. Okay. So there is a little work to do. No need to look at how the marquee scheme has worked if you're having problem. Merge these two, take out whatever I have just told. We first write down whatever we have from the data booklet, okay, as it is. As in this equation, we are not being told which one is the reactant, which one is the product. So we have to use the knowledge that the rule, it is a rule which has been given to you. It is the rule where the more positive is reduced and the less positive is oxidized, and then we just balance the electrons. Remember the final equation, we do not have to have reversible sign. It is a irreversible sign. This one we have worked so many times. I've given some details over here. I hope that you've got the answer. Now here also the same thing. You see, this part D and B are interrelated. D and B are interrelated. Same logic has to be used. It is that you've taken from the data booklet. Okay. Okay, so after having taken, you have taken it from the data booklet. Right. So from the data booklet, 0.00 minus 0.91. So this is going to be reduced more easy. Okay, we have it in paper 42 also. We are going to skip it over there. So the more positive inert value gets reduced. Here, dot and cross diagram, I hope you could have worked it out. First order, both of them are first order. Okay. Now we have something new over here, B third part. Please put a note over here. All right. I have told you some time back that to find the order, we usually have to do. We usually have to what we say. We usually have to do a practical and then make a table and then find out how it is changing. Okay. Then you may be called to work out the equations involved. You will have a slow step and a fast step. Over here, state and explain whether or not the reaction could take in a single step. So this is a question which is kind of a new one. You can see that we have already been given first order. Okay, so when we've given first order, here, this is the rate equation. By coincidence, the order of the reactions and the number of moles are the same. So if the order of the reaction and the number of moles are the same, then we can say that it can go in one step. I repeat again, if the order of the reaction with respect to the reactants is equal to or is the same as the number of moles in the equation which is given, then you can say that it is a one-step reaction. Part C, you have a graph. I hope that the graph is the same as trying to show over here. This is the graph. It is going to change from 2.05 it is going to become 1.8 multiplied by 10 raised to the power minus 4. Okay, there's a simple calculation to do. Okay. So the calculation is as follows. We have the initial rate per second. It is for 1 second, but it is here we have one for only 0.2. So I calculate how much will be used in 0.2 second, and then my initial minus how much I have used. I get N.8 for the subsource de moins 4. Okay. Remain constant means that you have reached equilibrium, because in this reaction, let's just go here. You can see that the reaction is a reversible one. Okay, you can see that the reaction is a reversible one. Here, note that the reaction is a reversible one. So, if it is a reversible one, of course, it is going to reach equilibrium, and then the concentration are not going to change. Only in irreversible ones do we go to maximum O to Z, O to 0. Entropy disorder, here we have not done it in lower 6 till now. For upper, let's just do a small recap. Even the lower students just listen to the recap because it is very important. Okay, entropy is disorder. Plus ou on a désordre, plus ou entropie li positif. Plus ou on a désordre, plus ou entropie li positif. Ok. Alors si nous prenons liquid water, nous pouvons couler tout 60. Nous pouvons tirer disorder, qui fait nous pouvons tirer disorder. Chemical energy is being lost during cooling. On peut dire bonds are being formed, which brings order. Ok. Alors, là, nous pouvons former des bonds, parce que là, nous pouvons faire cooling, des bonds pour former, des molécules pour comme closer. Ok. Alors, disorder pour diminuer, alors entropie pour une négative. Solid calcium chloride, nous avons strong ionic bonds qui finissent trap saban ions là, mais là, ils viennent and aqueous, the strong ionic bonds are broken, the aqueous solutions are mobile. Okay? Mais qui nous veut faire? Nous veut break band bonds. Aussi, qui nous veut faire? Nous veut faire solide, qui est bien compact, qui est bien en load, peut venir par mobile ions, comme un mobile ions capable de bouger in any direction. So this is how we look at. There's one simple method is you can relate it to the bond formation or the bond breaking. When bonds are formed, okay, when bonds are formed, you bring order. When bonds are broken, you bring disorder. Next, the change corresponding to the lattice energy of calcium chloride. You're taking gaseous ions, you're becoming a solid. Ions, gaseous state are free to move. You're making it become a solid, which is where the ions are not free to move. So the entropy change will be negative. So this part, you can learn it even if you're in lower 6. It is the beginning of the chapter. Okay. Delta G gives free energy, becomes spontaneous. Whenever you find becomes spontaneous, you have to know that delta G is 0. Okay. In fact, in paper 42, we have a question where we are saying delta G is equal to 0 and we are finding T over there. And if you have looked at the questions properly, you have seen that the Gibbs free energy equation is an important one. I hope that you can remember it over there. Okay, we just have to remember one or two things is that we need to do conversion because delta H is in kilojoule per mole. Usually delta H is in kilojoule per mole, but delta S over here we are not given the delta S, but delta S is usually joule. So there need to be a conversion to be done over here. Delta H has to be converted to joule. Delta S is already in joule. Like I said, there's a question in paper 42. Here now, phenyl ethanol. So you can see we have an alkyl group, we have a ketone group, and now we have a phenyl group. phenyl is also known as the arene, okay, because we have an aromatic group. You will see that I have let's look at the question first and then we come back. So we have a ketone, COCH3 ketone, then we have an alkyl, okay, and then here we have an arene. So now, this alkyl group can undergo only free radical substitution. Can undergo only free radical substitution. This ketone group can undergo nucleophilic addition. All right. It can undergo reduction to a secondary alcohol. Then positive Q4DNPH and positive thiouridine. Here, this arene, it can undergo electrophilic substitution. Right? But there's something which is very important. It has got a side chain. So if it has got a side chain, you need to look in your data booklet, part 9, the orientating effects of groups in aromatic substitution reaction, where you have COR, where COR is the ketone. You also have CHO, which is the aldehyde, and COR or CHO, they orient the nucleophile. Sorry, not the nucleophile, the electrophile. Okay, they orient the electrophile into position 3. So that's why I have counted now. You can count clockwise 1, 2, 3, 4, or anti-clockwise 1, 2, 3, 4. These two are the same. These two are the same. Okay. So phenylethanol can be synthesized using benzene. So it is an electrophilic substitution over here also. It is an electrophilic substitution. You have to form an electrophile. So here, the electrophile is CH3CO+. It means that the chlorine pulls electrons towards it, then breaks away. When it breaks away, it takes extra electrons with it to form Cl-. So the carbon becomes a carbocation. Okay. The plus is actually on the carbon. Okay. The plus is actually on the carbon, but while writing, you can write it down on the oxygen also. So I have given some details. See, I think in the marking scheme only CH2Cl, but it could have become CHCl2 or CCl3. But we stick to the simplest one, okay, which is CH2Cl, which is free radical substitution. Then we have the nitration of benzene, which is an electrophilic substitution. So this arene group is going to undergo all types of electrophilic substitutions. The ketone, like I said, is going to undergo its own reactions. Bromine water is test for, this is test for saturation, test for presence of C double bond C. In other words, test for unsaturation. Okay. But as we do not have C double bond C, we won't have that reaction. Phenylethanol reacts with HCl in the presence of small amount of NaCN. So this is the nucleophilic addition. It takes place at the C double bond O is going to take place at the C double bond O, where here I'm just going to write down something. If you are going to get C OH CH C N. Okay, so this OH. We have not been asked about it, but we can note that the product which is formed, this carbon is chiral. Okay, this carbon is chiral. So maybe ask about an optical isomer. So you have to prepare optical isomer over here. You please do it. Okay. I hope that I'm correct on what I have done over here. So I can see the C and the CH3. We are adding the CN. Double bond O will become OH. Yeah. So you have a carbon which is chiral. Okay. Now here again we have the phenyl ethanol, which is becoming the phenyl ethene in two steps. So in step one, because we cannot have a double bond just like that. There are two ways from where we get a double bond. We get a double bond by either elimination, where we have halogenoalkanes, or by dehydration, where we have alcohols. So we have a ketone. So the ketone, I can reduce it to the secondary alcohol and then make the secondary alcohol undergo dehydration to remove H and OH from adjacent carbon atoms. So H and OH carbons. Now this question could have been extended. All right, this question could have been extended where react with coal dilute So you can take the phenyl ethene and react with coal dilute KMNO4, or react with hot concentrated please work these out. Okay, work these two out. You for the coal dilute KMNO4, you're going to get a diluted a diol. Hot concentrated, when the double bond is going to cleave. On one side, you're going to get carbon dioxide and water, and on the other side, you're going to get benzoic acid. Okay, you're going to get benzoic acid because this is going to become COOH, which is going to become benzoic acid. Now, state the number of peaks in the C13 NMR of phenyl ethene. Okay, so we are going to move to phenyl ethene. So we have 6 carbons in benzene. All right, we have 6 carbons in benzene. If you have only benzene, listen carefully. If you have only benzene, then you are going to have one environment, because all the 6 carbons are going to give you one environment. But if you have a substituted benzene, then you have different environments. So this is a substituted benzene. Phenylethyne is a substituted benzene. So if this is carbon number 1, these two will be carbon number 2 because they do not have the same environment as carbon number 1. The environment of carbon number 1 is C double bond C. But the environment of carbon number 2 is not C double bond C. It is different. And that of carbon number 3, these two are going to become carbon number 3. They will be still different. So we have 1, 2, 3, 4 environments, or 1, 2, 3, 4 environments. These 2 carbons are the same. These 2 carbons are the same. But this carbon is totally different. So we have 1, 2, 3, 4. This is the 5th one, and this is the 6th one. Okay. Now, take your data booklet, go to number 7, typical carbon 13 chemical shift delta relative to TMS equal to 0. Okay. I'm going to look at phenylethene right now. We will have a peak at chemical shift range 110 à 160. I repeat again, we will have a chemical shift range 110 à 160. This will be due to the presence of either the alkene, okay, you have an alkene here, or the arene. These 2 functional groups are giving the same one, okay, the same peak. So, carbon 13 of phenylethene. Okay. So we have an alkene slash arene 110 à 160 ppm. Okay, okay. Now, this is number 1. Number 2 now, if we have an alkene or an arene, you will see on the table, you will have next to alkene or arene. This is my second one, my second peak, next to alkene or arene. So if I have an alkene or arene, I will have next to alkene or arene. If I have a carboxyl or a carbonyl, I will have next to carboxyl or carbonyl. You can see carboxyl c'est 110, 160 à 185 et carbonyl c'est 190 à 220. Après nous avons là-haut 25 à 50. Si nous avons nitrogen, ça carbon next to the nitrogen, pour next to nitrogen. Si nous avons chlorine and halogen or alkane, nous prenons next to chlorine. Si nous avons oxygène, nous prenons next to oxygen. Et over here, nous prenons oxygène sur là. OK? C'est-à-dire, nous prenons OH ou bien nous prenons ester linkage. Now here, this one. This is the carbonyl. Ça carbon, C double bond O. Là, c'est carbonyl. Mais automatiquement, nous prenons next to carbonyl. Okay? Automatiquement, nous prenons next to carbonyl. Ça, c'est un arene. Alors, automatiquement, nous prenons next to arene. Okay? Let me get input. What has happened? What has been given? Oh, so you can see. Maintenant, carbonyl, 190 à 220. Alors, automatiquement, nous prenons next to carbonyl, 25 à 50. Maintenant, arene, 110 à 160, c'est-à-dire que nous utilisons NaN next to arene, 10 à 40. OK? Mais il ne faut pas croire que Cambridge donne ça parce que next to carbonyl là peut déjà fini couvert sa région là. Okay, so it is quite easy Okay, I hope that you have understood it. I'm going back. Si mo an alkene, mo next to alkene. Mo an arene, mo next to arene. Over here, it is quite easy parce que mo alkene, next to arene, next to alkene, c'est la même chose. Après, le troisième là, peut venir arene. Here, mo carbonyl, mo next to carbonyl, et mo arene. Mais si mo arene, ça c'est arene, mais ça là, il est capable de tomber next to arene. OK? Ça, il peut tomber next to arene. Mais il est déjà peut tomber de carbonyl. Alors, Cambridge pas fin donne ça next to arene. Est-ce que tu peux faire bon, pas quoi, si tu peux écrire tous les quatre, je vous donne une faute parce que vous pouvez donner ce qui est là, peut être negative marking d'après ce qui Cambridge fait dire over here. Mais d'habitude, si on a deux carbones qui peuvent tomber dans même deux carbones qui sont dans deux différents environnements, écoute ça bien, si on a deux carbones qui peuvent tomber dans deux différents environnements, par exemple, ici, tu peux avoir next to arene, c'est 10 à 40 qui il paraît comme un carbonyl 190 à 220. D'habitude, nous écrire ce qui est plus grand. Okay, here, silver sulfide is insoluble in water. Première chose que je vais faire, je vais écrire une équation. Et on écrit l'équation là, on gagne Ag2S reversible sign 2Ag plus plus S2 minus. This is why I've written this part over here. And then I've replaced it here in the KSP. Okay, but when we are working it, okay, but when we are working it, we have to be very careful. Here, you will see Ag2S present 1 mole of S2 minus. So the concentration of Ag2S and the of S2 minus will be the same. La concentration pour N.16, c'est-à-dire N.16 fois 10 à puissance 2 moins 17. But 1 mole of Ag2S gives 2 moles of Ag plus, so the concentration of Ag plus will be twice. Okay, so you take care when you are working it. I repeat again, you have to write down the equation. The marking scheme has not given the equation, but you needed to write down the equation. From the equation, you will find out that 1 mole of Ag2S gives 2 moles of Ag plus and 1 mole of S2 minus. As it is in equilibrium, the concentration of Ag2S will be equal to the concentration of S2 minus because they are 1:1. But that of Ag plus, I have to multiply by 2. Okay, but when I write the expression, I do not put the 2 in front, I put it as square. But when we are finding values, okay, I square and I multiply by 2. So here, just give me 1 sec. So N.N6 moins 17, et donne-moi N.N6 exponential fois 17 fois 2, il donne-moi 2.32 fois 10 à la puissance de moins 17 fois 2.32 moins 17. Là, nous multiplions tout par N.N6 moins 17. Then only we get 6.24 fois 10 à la puissance de moins 51. C'est-à-dire, là, on peut travailler, ça va l'air de KSP là, on peut remplacer ici, ça square bracket là pour une common bracket, ok? Simple bracket. Et pas oublier objet square 2.32 fois 10 à la puissance de moins 17. Alors, combien on peut créer ici? C'est objet 2.32 fois 10 à la puissance de moins 17. Why is that so? C'est 2 moles of Ag plus are formed. Here, 1 mole of Ag S gives 1 mole of S. Yeah. To get this value, we replace in expression. Okay, how it works. Calculate the minimum volume of water needed to dissolve 1 gram of Ag2S under standard conditions. Okay, clear? And here we are given the dm cube. So here, in fact, when I look at this, it is concentration in gram per dm cube. Okay. So this is the main part. It is the 1.00, and the dm cube tells me that I have the concentration in gram per dm cube. But we are given the concentration in mole per dm cube. This is the concentration in mole per dm cube. So what I have to do, I have to convert the concentration in gram per dm cube into mole per dm cube. Okay. Sorry, the mole per dm cube into gram per dm cube. So what is concentration in mole per dm cube? So in fact, just write it down. Concentration in mole per dm cube is in fact concentration in gram per dm cube divided by mR. And then you divide all by volume. So this is what has been done. This is the concentration in mole per dm cube. This is the concentration in gram per dm cube already found. We divide all by the volume, and then we make volume the subject of formula. A pH of a weak acid, we all know, say square root. I could not get the square root sign. Square root Ka, concentration of the acid. So this is the concentration. Ka is given. Okay. So we have to look for H plus and then the P, pH. So here. And we all know that pH is equal to what? So pH equal to minus log extent concentration of this. So then you just replace in the. Now this part was a bit different from what you usually work. 5 centimeter cube of 0.20 mole per dm potassium hydroxide was added to 20.0, 0.20. So this is a alkali, a weak acid. When alkali and weak acid reacts together, salt and water are the products. Now, and the salt is in equilibrium, is in a mixture with the acid should be weak acid, we get an acidic buffer. It's something which is known as an acidic buffer, where an acidic buffer has got a weak acid and the salt. Now, we have the initial number of moles of KOH that we need to calculate and the initial mole of the acid. Remember that the acid and the alkali are reacting together. So the number of moles of the acid is going to decrease. So this is in moles of KOH taken, moles of HOBr taken, moles of HOBr at equilibrium. Okay, I will say initial minus how much has been used up. Now you can see that the ratio is 1:1. So here ratio of acid alkali is 1:1. Why it is 1:1? We have one OH minus and one H plus. Okay, so here, in fact, this is a mono basic acid. 1:1, right? So this is why we've not multiply where we are subtracting. 3 fois 10 à puissance de moins 3. Now, how many moles of the salt will be produced? So this is salt produced. Okay. Depends on number of moles of H minus used. I believe N is to 1:1. Okay. So you get N fois 10 à puissance de moins 3. So if you get all of these, you are getting 1 mark. Then for the second mark, no need to follow what Cambridge is saying over here. You have what you call a formula for buffer. Okay, so you can use the formula for the buffer. Okay, yeah, but in that formula of the buffer also you have the ratio of the salt upon the acid, so the same thing, and then you just replace. But the most important part is the how to get the first mark. The first point mark is not easy to get. You have 1, 2, 3, 4. You have 4 steps to get only 1 mark. So the KOH which is being added to the weak acid is reacting with the weak acid. It is decreasing the number of moles of the weak acid to produce a salt and water. So the initial number of moles of the weak acid is going to change until an equilibrium will be reached. And the number of moles of KOH used will be equal to the number of moles of the acid used, which is also equal to the number of moles of the salt which is produced. So once you get this part, then you can replace in the formula of buffer. Yeah, this part we are just going to skip it. There's nothing to discuss. Okay, transition elements. Now, we are already being told that they are oxidizing it. Okay, yeah, so here what we have to do, so just 1 sec. So we need to again choose equations. So I have been told that the reaction is already feasible, so I no need for me to find out the E0 value. But those who have problems with this type of question, work out the E0 value. So here I'm being told that when chromium, that is when, not chromium, sorry, one sec. When SN2 plus is being made to react with acidified potassium dichromate, the SN2 plus is getting oxidized to SN4 plus, right? So what I have to do, I have to look for the equations where I have SN2 plus and SN4 plus. Okay, so these are the equations for SN2 plus and SN4 plus. Now, secondly, I have to understand that when the chromium is in the +6 oxidation state, it is orange. Okay, so if I have to calculate this, it is 2x minus 14 is equal to minus 2. 2x is equal to minus 2 plus 14. 2x is equal to plus 12. X is equal to plus 6. And here it is plus 3. So I've taken down these two equations from the data booklet. I don't need to learn them by heart. Then what I have to do, I have to rearrange them. I could have rearranged them with respect to the E0 value, where the one which has got the more positive one is going to get reduced and the lesser positive one is going to get oxidized. But over here, I'm also given the data that SN2 plus is becoming SN4 plus. So this equation of SN4 plus SN2 plus, you are going to reverse. This one, you're going to keep it as it is. Not only that, this one you have to multiply by 3. This one, no need to multiply. Why do you multiply by 3? You multiply by 3 so that you get 6 electrons, and then the electrons will be on the opposite side, and then they are going to cancel. Now, we could also have been given the equation about Mn. So we all know that KMnO4 in fact is MnO4 minus, and it is purple in color. So we could have taken this also. May have asked us to work out with this equation. So MnO4 minus, so x moins 8 est à moins 1, x est à plus 7. So when it is in the +7 state, it is purple. But then when it becomes in the +2 state, it becomes colorless. Now here, what is interesting is to work out the final equation. So for this one, you're going to reverse and multiply by 5. This one, you're going to leave it the same, and then you have to multiply by 2. Please, those who have problems with these types of questions, do what I've, from where I have stopped, look for the E0 value. You should have positive E0 values. Now here, ruthenium has got +2. So Ru is +2. NH3, 0. Cl -1. SO2, the new molecule, c'est 0. Alors, là, nous faire sa partie-là, nous pouvons gagner plus 2, retient 1. Et equal to plus 1. Et ça, plus 1 là, c'est ça. Overall charge. C'est ça, overall charge. Alright? C'est plus 2 de ruthenium et moins 1 de chlorine. C'est pour ça que nous gagnons plus 1. So, just we have just taken the theory which is given and just put in a square bracket, because a complex is always shown by a square bracket. It is, let me just have a look here. 4, 5, 6. So 6 coordinate bonds. 6 coordinate bond, it has to be an octahedral. Okay, so here you have to draw octahedral one. Okay. Now these octahedrals, because they are monodentate ligands, okay, so they could have given me optical or cis strands, but over here mostly it is cis strands, okay. So just look at the marking scheme to get the cis strands. Here, this fifth part, we have seen it many times. We have explained it many times also. Now, we are at proteins. We all know that proteins are made up of amino acids. Now, what is important is look at the molecule. This is the general formula. So we start from the left. Alors, ça c'est COO. La limite minus parce qu'il peut montrer nos hydrolysis. COO minus. Alors là, maintenant, CH. Ça c'est mon R groupe. Alors, mon R groupe c'est CH, CH3, C2O5. C'est-à-dire ça c'est C. Là, moi, un hydrogène. Et là, moi, un hydrogène. Là, moi, un carbone. Là, moi, un CH. And CH2. Lower students, on peut trouver, peut faire comme si un coude, et de là où on a un CH2, et le final, on a un CH3. Okay. Ici aussi, qui est là. Là, qui est là. On a un carbone. Là, où qui est là, on a un hydrogène. Là, qui est là. Là, qui est un carbone. So now I hope that you can see that COOH, okay, COOH, CHR, then NH2. Now, the NH2 has become NH because there has been condensation, polymerization, or condensation reaction where from the COOH, okay, from the COOH, so here, OH is lost. Here, H is lost. Okay, the CONH is known as the amide linkage. Here you can see we have a CH2 here. So I have a primary alcohol. Here the R is H, because what I have NH. So this is the C, the CH, right? So please work it out. So we have carboxylic group. We have a base here, NH2, which has come to NH3 plus. When this is plus and this is minus over here, there is a question being asked somewhere. So they are going to form ionic bonds. The NH and the OH, okay, the NH and the O from the OH, okay, they can form hydrogen bonds. This alkyl group can form van der Waals forces. In your marking scheme, you have been given London forces, but London forces is not for CIE, for those giving exam for this year. So those London forces can be replaced by what we call as van der Waals. So we will have the cleavage of CONH. So then here, this one is going to break one here, second over here. So in fact, you are going to get 3 amino acids. Like I said, in your marking scheme, you have there's London forces for you. It is Van der Waals forces. Polyester, you can write for yourself directly from the notes. Okay, here we have an ester. Okay, complete the equation for a reaction in which butamben acts as a base. Okay, so if it is acting as a base, so here we will have H plus and the NH2 gets converted to NH3 plus. Now we can also put HCl. So when we put HCl, we have a small change over here. NH2 will remain as NH2. The NH3 is going to remain as NH3. The plus will be plus. But then we will have the Cl minus which should be included so as to balance the equation. Now, a question whenever you are stronger or weaker base, what you have to look at, you have to look at the availability of the lone pair. If it is delocalized, it is not readily available. So it will not accept H plus ions readily and is a weak. See the theory behind it. So we all know that the lone pair on the phenylamine, it is delocalized into the benzene ring. And when it is delocalized the benzene ring, remember, it makes the benzene ring become more reactive. Okay, but the lone pair is not readily available over here. And then the benzene ring becomes more reactive, and you have to look at the orientation. And when you look at the orientation, it is 2,4,6. Phenylamine and phenol, they are 2,4,6. Okay, they have given you the details. Let's just look at it. Okay, we come to the splitting now, so the NMR of butamben. So see, we are working with butamben. So this is A, B, C, D, then E and F. So in fact, we have 6 environments. I hope those who are having problem with NMR, 6 environments. So this is one hydrogen with one environment. It is attached to the same carbon. This is attached to the same carbon, second environment. Same carbon, third environment. Fourth carbon, fourth environment. Now we come to the benzene. Wait. There's more mistake here. There will be 7 environments. Okay, so 1, 2, 3, 4, 5. I hope this is okay. Oh, no. It was good. For the benzene, they are going to take it as one in whole. In fact, there will be more environments. Okay. In fact, by theory, there are lots of environments, but when you look at your benzene ring, it is considered to be as one environment only. So 1, 2, 3, 4. All the hydrogens in the benzene will be the 5th one, and then the hydrogens on the NH2 will be the what we call the 6th one. Okay. Now, state the number of peaks in the spectrum that show a triplet splitting pattern. Now, if you have a triplet pattern, it means that you are attached to a CH2. So you can see that this HA will give triplet as attached to CH. This is the first one. Secondly, look at HD. HD will give a triplet as it is attached to H. So HA and HD are attached to CH2s. So this HA and HD, they are going to give 3 triplets. Okay. Now, we are going to do a little bit of work over here. So HA, have your data booklet in front of you. HA will be a triplet (0.9 à n.7 ppm. HB n triplet ou bien nous pouvons dire multiplet. Ici pour 0.9 à n.7 ppm parce que banana petom de ban alkyles. HC il a DD hydrogène, c'est-à-dire 4 hydrogènes total sur le côté pour N impact. Ici pour 0.9 à N.7. Mais HD, on a déjà fini de connaître qu'il y a une triplet. HD, on a déjà connu qu'il y a une triplet. Okay. Stellarly and triplet, li attache avec O. Et bien, il attache avec O. Alors, pour lui, c'est 3.2 à 4.0. A, B, et C, they were counted as alkyls. Okay? Mais D, li directly attached to O, ça veut dire pour une alkyl next to electronegative atom. On va dire là, A, B, et C, c'était pas alkanes. D n'est pas un alkane parce que d'un côté gauche, il est attaché avec un E, alors li c'est alkyl next to electronegative. That's the HE. Lui, c'est un NH2 qui attache avec un benzene ring. C'est lui pour singlet, un pour un singlet. Là, pour un avril 9. Lui pour 3.0. 6.0. Puis finalement, nous prenons HF. Ici pour un singlet. Parce que NH2, ni lui amène splitting, si double bond O pas amène splitting. Et pour lui, c'est 6.0 à 9.0. Et attache to aromatic ring. Alors, si nous mettons D2O, okay, ce qui peut arriver, c'est NH2 becomes ND2. Il derive ND2. P disappears. Spectrum, obligé de faire trial and error, trouver une valeur là, les grands. OK? Alors, si une valeur là, les grands, et pas pour par là, je me rappelle que CH, une petite chose qui est simple, je rappelle CH free, il est 15, OH plus, il est 17, then we have CH free, CH plus clearly 29. Et maintenant, COCH 3 place là, du coup. Voilà. Alors, c'est 12, 12, 12, 12, 24, 24, 16, 40, 43. Okay, so you have different peaks. Some of the peaks, they are common peaks. You have to learn them by heart. Okay, so this gives us, this ends this paper 41, almost 1 hour it took. Okay, so we end up this one, paper 41. We are just going to take a small break. Okay, we'll just take a small break of 15 minutes and then we meet at noon. The second paper will go a bit faster because we are not going to dwell on the same details again. Those who had problems with the data booklet, what we call electrochemistry, just give me a feedback. I've worked one or two, I've just told you how to work them out. Give me feedback. Okay. I hope that whatever questions you had told me, I had 1 or 2 questions. I've not looked at the list. Okay, just let me have a look at the list quickly now. I was given 5B, 5B part 2. I did talk about it. 8A part 1 part 2. Okay, so the cleavage of the CONH bond. So just it is because of it is in the skeletal that you may be having problem. Okay, so just break the CONH bond. Okay, so here it is going to break over here. Let me just put something. So it is going to break over here. One, and the second is going to break over here. Okay. Yeah. So I hope that these are the free ones because I have not looked at the marking scheme for these. So these are the free isomers. So here you will have OH, NH2, OH, NH2. These all groups are going to remain the same. OH, and here this is going to become NH2. Okay. And then we had 9C. A, 9B. 9C, second part. So 9C, second part. Okay. Circle the protons responsible. So I've just explained to you how it has to be and how we need to get the two peaks. So the two and these two are interrelated. So please just give me feedback for those who had problem with 5B second part, 8A second part, 9, question number 9A and 9C, if it is okay. There are 1 or 2 students who are still having problems with what we call as NMR. So just give me a small feedback, and that with electrochemistry. The pH, you will see that I've looked at it in details this time. Last time we went a bit faster, but this time we're going to be detailed. In paper 42, we are going to look at it more. Okay. So just give me a small feedback. It is 11:47. We meet at 12:05. Okay. We meet at 12:05. Okay. You can remain login just, and then we meet at 12:05. second session. Again, have your data booklet with you, please. Question number 1. You can see both sides there of platinum. Why that's so? Is because ions are concerned. So ions only are concerned. So whenever we have only ions which are concerned, we have to add what we call as platinum as a record. If we had a metal, then the metal would have been used. Nernst equation again. So here, again, we are not being told about the products, but we are given the idea what half equations to choose. I've chosen them from the data booklet. So the Mn3 plus 1 is most positive. It is going to remain in the reduced form. The Br21 is going to be in the oxidized form. So it is going to be plus N.49 retiré N.07. Et 0.42. I'm getting 0.42. I don't know if the data booklet of that time was a bit different. Okay, if anyone can give me an idea, but I'm getting plus 0.42. The last paper also I had in data booklet got plus 0.6, but it was giving something else. So I'm just going to use this one, minimum of 2 SF. This is the answer. So now you can work it out, all right, where you have to multiply by the common factors. Question number C, this part I have worked out. I've worked it out for all of you. Please, on the left-hand side, this is from the marking scheme. This is right-hand side from how I have worked it out. Please have a look. Part D, something like that was discussed. 2A, simple definitions. 2B, okay, we have something like that in our notes. So what we have to do, we have to change concentration of OH minus, all right? So, and then we have to take the same concentration of CH3Br, right? And we have to take this same temperature. So here, CH3Br, we are taking it in excess as it is not controlling the rate. Okay. Different initial concentrations of OH minus have to be taken. Here, what we can do, we can vary the volume of stock solution OH minus and water. Just like in rate of reaction, then the concentration of OH minus is going to change. Here we are going to use a thermostatically controlled water bath. Here we are going to use a okay, we are going to titrate. I would like to titrate against HCl. Okay, when you're going to have the endpoint, then you're going to find the concentration of OH minus remaining, and then you can plot a graph. And when you plot a graph, it has to show that it is first order. Here, question number 3, again, we have about pH. I have worked it out in details. So we are looking for concentration of H plus, so we do inverse log of pH. Then we are looking for pKa, so we have to look for Ka, and then from Ka we go to pKa. Buffer, okay, so here a buffer, it minimizes change in pH when you add acids or alkalis. So if you are adding acid, is H plus, NH3 plus is going to become NH4 plus, but if you are adding OH minus, it gives you NH3 plus H2O. You can also use H plus OH minus give H2O because it is neutralization. We all know Kw is concentration of H plus and OH minus, so you can find out H plus where H plus and OH minus. So here the concentration of H plus is equal to the concentration of OH minus, okay? So it is going to become square, okay? So if I'm just going to work it out a bit. One sec. Square bracket H plus square bracket H plus to the square equal to K W, and then you just find the H plus one. Here again, same thing. You have to find the value of Kw, but Kw is H plus OH minus, H plus is OH minus, so it is Kw H plus to the square. Yeah, made a small mistake here. Simple bracket. Okay, come to this question. So this is a new one, entropy. So delta S naught, it is same as what we already know. Sum of SL products minus sum of SL reactants. Because we are given S, so delta is difference. Then you have the question where you had the theory in paper 41. Here you have a calculation where for the reaction to be feasible, the delta G naught has to be 0. And then you make T become the subject of formula, but you have to convert the delta H naught Okay, you have to convert delta H naught from kilojoule to joule, because you can see delta S naught is joule and delta H naught is kilojoule. So this small change you have to do. Okay. Solid lead trioxide can be made by heating lead metal in air. So what are you doing? You're using air, you're using gas molecules. So when you're using gas molecules, disorder decreases. When disorder decreases, entropy becomes negative. This one we're just going to skip it. Let's look at over here. Okay, we can skip it. This one also we can skip. Transition. Okay. Part D, we have again an electrochemistry. So I've given the equations. Here we are already being told that Fe2 plus we are taking. So the first equation has to be reversed and multiplied. So no need, again, we have both of them working over here, but here, as we have been given the reactants, it's better we go with the identity of the reactants. The identity of the reactant is Fe2 plus, so the first equation has to be reversed, so automatically the second equation has to be kept as it is. But we have 2 electrons and 1 electron, so we multiply by 2. Okay, and we are going to get plus 0.77 volt. Case tab. In case tab, we do not include concentration of water. You can see that it is a small case tab value. So maybe if you would have got a question about where the equilibrium lies, the equilibrium would be lying more towards the left-hand side. Okay, so tab value equilibrium must be lying the left-hand side. Here. Benzene 1,4-diol chloride. I've counted to show how we got the 1,4 and 1 diamine. I could have also done 1, 3. Does not make any difference. It will be the same clockwise and anti-clockwise. So remember over here you are going to get condensation, polymerization. Okay. You are going to lose HCl from NH2. Simple form 5 level it is. Cl from Cu. L, Co, and H. Amide linkage. So this is how it will be between that. So you will get 2 repeat units. Okay, so CONH, CONH, then this, then NHC double bond O. Okay, so it is a polyamide condensation. All CONH can be hydrolyzed. It is biodegradable. Benzene 1,4-diol chloride from benzene 1,4-dicarboxylic acid. So this is COOH is becoming COCl. Okay, you may be asked, you can get white fumes. Here are the observations during the reaction of HCl. White fumes of HCl are seen. Here, very simple one. Nitration, nitrobenzene, electrophilic substitution, NO2 to become NH2 reduction. I don't know why Cambridge has not put concentrated. Sometimes they ask about concentrated. I think we should add the concentrated one. Primary, secondary, and tertiary, we have done it properly. Okay. First one is only the sequencing, then alpha and beta when they revolve around themselves. We have the hydrogen bonds which are formed between the CO and the NH. Then they fold again. Okay, they fold again, and then we have more intermolecular forces which are formed between the R groups. So here, Cambridge has given covalent dipeptide whatsoever. We are going to go according only to covalent. Now, in the secondary, we have the hydrogen bonds between the CO and the NH in the amide linkage. This is the amide linkage. Okay. Then let's come to the tertiary. In the tertiary, you will have the covalent, the hydrogen between CO and NH in the amide linkage, plus all the other, okay, plus all the other bonds like the Van der Waals forces of attraction, hydrogen bonds, and the ionic bonds, and the disulfide, okay, linkage, okay, which will be present due to the formation of these bonds with respect to the R groups. This is mostly paper 2. Okay, we're just going to skip it a bit. Here again, we are talking about acidities. So when we talk about acidities, there are two lines which are important. We need to lose the H plus easily, and then it should be in the solution for a long period of time. That is, the lone pair should not be readily available. When the lone pair should not be readily available, we have to look for this word, delocalization of lone pair. So this part will be important, where we have the delocalization of the lone pair. When we have the phenol, here we have the delocalization of the lone pair. Okay. So hexanoic acid, it will be greatest. Okay, and then among those two, you can see that hexanol is the least acidic. So in phenol, we have the delocalization. That is why it is not readily available. So compared to hexane-1-ol and phenol, in hexane-1-ol, the lone pair is readily available. In phenol, it is not readily available. In phenol, you will have H plus ions in the solution for a longer period of time. All right. Now we come to, we are not going to look at the peaks for the time being, but we are going to look at what we have in front of us. So we have a hydrogen here, which is HA. Here it is HB. Here we have free hydrogens, which will be HC. And here we are going to have HA because it is a mirror image. This HA will be a singlet because there are no hydrogens in the neighboring carbon. And also it is COOH, right? So it will be 9.0 to 13.0. So this one, and then we are going to look at what Cambridge is dealing afterwards. So when I'm looking at the question over here, I need to find this one. Then we have a CH. This one will be 0.9 N.7 around there. And change also because we have an oxygen in the molecule. This value of 0.9 à n.7, c'est when there are no oxygens, okay? As they are a bit far, wait. I made a mistake over here. So this one is 2.2 at 3.0 because it is next to a C double bond O. It may be greater than 2.2 at 3.0 because in 2.2, 3.0 we have only one oxygen. Okay. But here we have two oxygens because it is carboxylic acid. The CH3, it is CH3C, then C double bond also it is mosaic alkane 0.9 n.7, but it will be close to the n.7. Now, these three hydrogens are attached to a carbon which has got one hydrogen. So these ones should be doublets. These ones, nothing there, so singlets. Singlet. Singlet. This one has got a hydrogen, so I said doublet. This one has got three hydrogens. Thus, this one should be quartet. Without looking at the graph, we have to come to these ideas at least. So you see, we have the doublet. Yeah, like I said, quartet. And here, douze points. So you can see we are getting what is there in the data booklet. So this is the carboxylic acid. This is alkyl next to bond O. And this one is all. Okay. If you remember in the earlier papers, we had a TMS peak over here. It is not shown, so it is not a problem. So I hope that this part was okay. And how we got the quartet, quadruplet. Carbon 13 now I've counted 1, 2, then it is a mirror image. We have a mirror image over here. Here we do not have mirror image. So 1, 2, 3. Oh, wait. Yeah. We have a mirror image. So this is the H here, that the CH3 is down. So again, a mirror image. 1, 2, then this is the 3, and then it becomes 1 because it is CH on top, CH3 at the bottom, COOH on both sides. This question was a bit tricky. Question number 9. Remember here we have 3 pi bonds. So if you have 3 pi bonds inside the benzene ring, it comes to 6 electrons. 2 electrons here, which are delocalized. So 6 plus 2, 8, and then 2 again. So the total becomes 10. So this is how you get the total. Yeah. Okay, so 2 electrons, 2 comes to 10. Here, this is something new. Predict the NH2 bond angle in the NH2. Okay, so actually, here in the NH2, right, you can see you have one bond with hydrogen, second bond with hydrogen, third bond which is going to this carbon. Third bond is coming to this carbon over here. So this is an right. So we have free bonded pair, and it needs to have free bond pairs and one lone pair. This is what we should have got. So when we get this part, we should have had what we call as pyramidal 107. But the marking scheme is saying 120 trigonal planar. Why it is trigonal planar? This is a new concept. Learn it. Presence of 2 electrons which are delocalized. So when they are delocalized, it means that they are free to move. So when they are free to move, it does not mean that it is there always. So this is why 120. All right, so instead of OH, you put Cl, and then you put ammonia under pressure. Here we are doing what we call as hydrolysis. This is acid hydrolysis. Acid hydrolysis gives you a carboxylic acid. Alkaline hydrolysis gives you salt. Okay? So here you will get carboxylic acid. Here you get salt of carboxylate. Right, so your CO is becoming CH2. So because here you have CH2. Remember, whenever you have a kind of an elbow, it is CH2. So here your C double bond O is becoming CH2. So it means a reduction has taken place. Again, now we are talking about basicity. So basicity means a base which is accepting H plus. So it means that the lone pair should be readily available. But if the lone pair is delocalized, it won't be readily available. So we have to look at where we have a delocalized lone pair. Okay, so this end up today's marking session. Now you listen carefully. We are going to change a bit of working now. You will have to attempt maximum paper 4. Listen carefully. You have to attempt maximum paper 4. When I say maximum paper 4, let's say from 2005, if you can. Okay, 2005 to 2009, 2007, you have only one variant. Otherwise, you have two variants. Please work out all the variants. Now, what you are going to do, you are going, especially this is for grade 13 students, grade 12 students, you are going to keep on working. We are at November 19, so you're going to work November 18 now, okay? But grade 13 students, if you have finished with grade November 18, November 17, November 16, keep on working. And if you have a problem in any question, WhatsApp it to me. Okay, WhatsApp it to me so that I can solve it, because it is going to take lots of time to come with all these marking schemes if I have to look at them one by one. So instead of you having a you're lagging behind with explanation, you work any paper, send the paper with send a good snap of the paper with the year where it is. Tell me what is the problem, what you are not understanding, and then I will come back to you. Okay, so start doing that. Otherwise, we are going to correct November 18 for our next session for paper 4. Paper 51 and 52, no one has come forward with problems. So what I'm going to do, I'm going to work out the marking scheme, then try to add whatever has to be added, put on the graphs and all. If you have problem with that, you come back to me. Same for paper 2, same for paper 4, same for paper 5. Grade 13 students, right now it applies only for grade 13 students. Grade 12 students, you keep on working from November 18 because we are going to do November 18, November 17, November 16. You keep on working like that. Okay? For the time being, grade 13 students, you work and you send your problems. We will have the next session on Tuesday. Okay, Tuesday, 6 o'clock. November 18, paper 41. Okay, so Tuesday, 6 o'clock. November 18, paper 41. Only paper 41. Okay? But if you're working other papers, you should be working other papers, be it paper 2, paper 4, paper 5, be it even be paper 1, it depends on where you are. I will recommend you to do a mixture of papers now. Mix those papers 1, 2, 3, 4, 1, 2, 4, 5. Why is that so? Because in paper 4, you have paper 2. In paper 2, you can get something which is related to multiple choice. Okay? So you have to take from 2020 to 2016, try to work out all the paper 1s, paper 2, and paper 4 before you go for the exams. I have already sent you March 2021 also. Okay, so you need to work that part all. Okay, clear? I may not be replying to you because sometimes I am working with SC students or I'm not available online, but I will come back to you because from now onwards, I myself am telling you that we are going to change the way of working. You're going to send your individual problems. The correction will keep on going on. Like for Tuesday, we have November 18, but you have to step up a bit now, okay? You have GP, which is comprehension. The essay is over. So step up your work because remember, you have also physics to look at. Okay, so we end up over here. I see you on Tuesday now. A bit later, I'm going to send you all the marking schemes of the paper we discussed today. Okay, so, and please give me some feedback about how you work for the paper 4. Okay, grade 13 students, please give me feedback for the paper 1 and paper 2 of today. Okay, bye.